So good afternoon, everyone, or good evening, and welcome to this second NEASQC webinar. It's one of a series of 9 between now and February 2022. I'm Pascal Bernier-Brunner. I'm the communication leader for the NEASQC project, and I will be your host today. This webinar is recorded, and you will receive the link to the recording on Monday. It's in listen-only mode because we have a lot of people registered, but you can use the Zoom Q&A panel to ask questions to the speakers, and you will see also the questions asked by others. You can upvote them, you can comment on the others' questions, and you can also chat with the other attendees for more informal exchanges. So before I hand over to today's speakers, I would like to introduce the NEASQC research project and our use cases, very briefly, I promise. So NEASQC stands for Next Applications of Quantum Computing. It's a 4-year project that started in September 2020. It's funded by the European Commission's Horizon 2020 program, and we are actually part of the quantum technology flagship. And we are a multidisciplinary consortium of 12 companies and research labs. You can see the logos here. And our objective is to boost practical applications of quantum computing in the NEASQC era. So practically speaking, this means that we are, I think we have some echo. Can you please be on mute? Thank you. So yeah, practically this means we are investigating 9 NEASQC compatible use cases. All use cases are endorsed by an industrial partner and investigated by an integrated team of industrial and academic partners. So we have use cases in three domains. The first one is chemistry with CO2 recapture and drug discovery. And if you have an interest in those use cases, you can attend our workshop at the EQTC conference I think it's on the 1st of December. Then the second domain we cover is machine learning and optimization. That's where we are today. Actually, we had a webinar about reinforcement learning, the reinforcement learning use case last week. Then today it's about hard optimization problems for energy management. And next week we'll have a webinar about the financial application use case. And the week after that about HPC mesh segmentation. And the last domain is symbolic AI and graph algorithmics, which covers quantum natural language processing, quantum probabilistic safety assessment, and quantum rule-based systems for breast cancer detection. And I would like to stress that each use case is committed to develop open source programming libraries. And the project as a whole is very committed to building a community with potential users of industrial NEASQC applications. And well, that's why we are organizing this webinar to share our knowledge and to exchange beyond the project partners. Oops, sorry, I was too fast. Oh dear. Sorry for the fumbling with the slides. So let's get on with today's agenda. First, I would like to introduce Dr. Vedran Dunjko from Leiden University, who will moderate the Q&A and discussion today. In our project, he's the work package leader for the machine learning and optimization use cases, and he deserves big thanks because he's not just the moderator. He organized this webinar and all our other webinars in November. So Vedran, could you explain how you built this agenda with 2 speakers, a guest speaker and a NEASQC speaker?
Right, thank you very much, Pascal. So as you clearly explained, the entire NEASQC project is all about bringing together industry with academia in order to tackle problems which are relevant for industry and society in general. And in the writing of our proposal, we of course wrote the best ideas we had at the time of how particular problems could be tackled using quantum technologies. But time moves on, and quantum technologies develop very rapidly, and very often we expect that the solutions are not going to be the most obvious ones. So the idea here is to invite speakers who are developing cutting-edge technologies, quantum technologies, to present their ideas on what quantum computers are good for without worrying too much about direct matching between the particular use case and where quantum technologies go, but rather have an open mind. So they will present their work, and we will present with our collaborator from, in this case, the French electrical companies sector, electrical management sector, the problem. And after that, we will have a brief discussion of 20 minutes to see how things mix and match, whether we've found something new, some interesting new way to connect quantum computers with our problems, or maybe not. So this is this idea to have an open mind to all problems and to everything which is possible and impossible. So with this, I think I will go ahead and introduce briefly our two speakers. So as mentioned, we have an external speaker, Alejandro Perdomo-Ortiz, who is really one of the best known researchers of his generation, certainly in various methods for quantum optimization. And he will be followed by our industrial speaker, Wim Van Ackooij, who is also an expert in optimization, but now in the classical world. So without further ado, Alejandro Perdomo-Ortiz did his PhD and master's in Harvard University. And for now, over 12 years, he's been working and developing quantum algorithms, but always with having in mind his eye on real-world applications and making a real-world impact rather than doing just theory. He's from the beginning been involved in collaborating with industry. He's worked for NASA, started his own consulting company, so he really has something to share with us. Alejandro, you have 40 minutes. I will show up as a face like some 5 minutes before the end, so you have some idea. But I will not be interrupting you otherwise, and I'll be moderating the questions and only interrupt you in the case that there's something technical or urgent happening. Please, thank you very much for coming, and take it away.
Thank you, Vedran. Thank you for the kind introduction and for the invitation. So let me start sharing my slides. Let's see, let's share this one. Can you all see the slides, the full presentation?
Yes, yes.
Okay, wonderful. Yes. Okay, let me just move this up a little bit. Okay, well, thank you everybody for attending. Yeah, so as Vedran mentioned, I'm very, very excited about this field of, I really like the vision of this program in the sense that one of the things that you realize through this talk is that we're still trying to figure out what is actually the key application for quantum computers. And that's basically what I've spent kind of like my entire career. For the last 14 years, I've been thinking about how to use these quantum technologies for optimization and for machine learning. So the title of my talk is Enhancing Machine Learning and Combinatorial Optimization with Quantum Generative Models. Hopefully at the end of the talk, you will get an idea of what all of these keywords or these buzzwords are about. And I'm currently at Zapata Computing. So that's where actually I lead a team of scientists, and as you're gonna see at the end, and I'm now the Associate Director of Quantum AI. So with that, if you have any questions about Zapata, so feel free to email me later and I'll be happy to share more about the company as well. So let me just give you a little bit of an outline of what the talk is about, or what is kind of like my goal with this talk. Is one of the questions that has been very close to my heart is this question of which are these non-obvious applications that could be promising for quantum advantage with these near-term quantum technologies. So notice that I put in parentheses non-obvious is because, let's say in our field, it is known that the particular case of quantum applications or quantum data or applications where actually, for example, quantum chemistry in materials, it is known that it looks like it's a better fit for these quantum technologies in the sense that you have a quantum computer matching the complexity of a quantum molecule or a quantum system, materials in material science. But actually the case of machine learning and optimization is not actually quite there yet. I mean, these applications come from the classical world. So the first question that might come to your mind is, why would I even think that actually a quantum computer might help? I mean, this problem with classical data. So I can understand why a quantum molecule might benefit from a quantum device, but it's not clear why actually a problem, a classical machine learning, as you're gonna see here, or a problem in optimization, like the energy problems that Vin might be discussing in the next in the next section. What would the benefit even from quantum devices? So that's basically what we spend most of the time actually trying to figure out. I will present actually an example in, actually I decided for the purpose of this talk, I will skip this example in a supervised machine learning, although we will be using the tool, so I will be introducing that, but I decided to skip that piece just so I give more emphasis to the optimization part, that I think that's the one that maybe is most relevant for the second half of the talk by Vin. So with that, but if you're curious about actually maybe how you can use these quantum devices to test and to generate high resolution images like this MNIST data set, so you can look at this reference. But in particular, I'm gonna be focusing for the most part in this, on these second references here that you see in the middle. So another thing is if you're more curious about actually some of these perspectives that I'm gonna present here, so you can take a look at this perspective article that actually the question from the editor is, what would you do with 1,000 qubits? So if you're curious about that, so take a look at that where we present actually our approach and the approach that we follow at Zapata and in Quantum AI about actually approaching these real world problems. So with that is, so what you will find in this talk is that definitely there is an importance for designing new algorithms. So we don't even know those algorithms, so we're still developing those algorithms. There is actually the need for like very robust software that can actually deploy this at a scale at the industrial level that you're interested. And of course, the hardware development is what makes all of this possible in the long term, in the medium to long term, where actually we are planning to run all these algorithms that we are developing. So let me just give you a little bit of overview or where specifically in machine learning we're focusing right now. And that's basically, this coming from one of the insights. And as I said, when I was still at NASA, one of the questions that I had with one of my PhD students was, machine learning it was as hot as it is right now. I think I'm talking about 6 years ago, so not too long ago. And the question was, even in the quantum community, we were seeing all the applications coming for quantum computers in machine learning, but what we realized is that most of the applications were in the field of what is called supervised learning. That, as you're gonna see, is actually is different from what I'm gonna be talking about here. So what we decided and it's still the view that I share, that I openly share, is that we decided not to go with supervised learning, although it is the hardest and is actually the one that you will find most of the applications in the industry. What we realized is that we wanted to go with the hardest applications in machine learning. And the reason that the toughest applications, toughest from a computational perspective, in such a way that we can actually have a slight chance of helping with a quantum computer. So what we figured, or what we realized back then, is if we try to use quantum computers for supervised learning, the timeline for us to make an impact there is going to be much, much longer. So since in my career, I want to see these computers actually making an impact before I die, I decided, okay, so let's go with unsupervised learning. And in particular, we're going to focus on a particular type of models that are going to be called generative models that I mentioned here in the top at the banner. So this is actually, we were happy to see actually where we took the decision. This is this paper for 3 of the fathers of pretty much the founders of deep learning and all this success of machine learning that we see in the news, Yann LeCun, Joshua Benyo, Jeff Hinton, that they were kind of like saying pretty much our intuition, that is, unsupervised learning has been overshadowed by the success of purely supervised learning. In the news, you would see all over the place applications of machine learning in the supervised learning, but actually where they expect to have, where they expect most of the impact is, we expect unsupervised learning to become far more important in the longer term. And the reason why it has been overshadowed is because it's much more efficient computationally. And then, so basically we don't want to compete against supervised learning. We want to tackle the hardest problem. So that's why all the work that you see, all the publication that you see coming from the group, for the most part, are in this field of generative models and in particular supervised learning. So just a recap, maybe for those of you who don't know that much about machine learning. So let me just briefly mention what supervised learning is about. So this is the one that is the typical one. And you will see, maybe you will get an idea why it is actually much easier than the one that I'm going to be discussing next. So in the supervised machine learning setting, so the important thing is that you have data. If you don't have data, then you don't have a machine learning problem. So this is called the data set. But the crucial thing in supervised learning, as the name indicates, supervised. So there is a teacher, and that teacher is the labels. So for example, if I give you an image of a dog, I tell you that I'm giving you a dog. If I give you an image of a cat, then I tell you that I'm giving you a cat. And after showing you many dogs and many cats, the type of model that you would build a mathematical model, in this particular is a deep neural network or a deep convolutional neural network that is used nowadays. And then after I send you an image of a dog, the robot of the model, what is supposed to say, this is a dog. Why? Because you show me many dogs and it looks like a dog. So that's actually how supervised learning works. So at the end of the day, you are only being judged, or the robot, the performance of the robot is only being judged if it can decide whether it's a dog or it's a cat or it's being able to classify. So this is one of the examples in supervised learning is called classification. So notice the story is completely different in a supervised learning. So that there are different flavors of unsupervised learning. Here is one in clustering. That is actually when you're giving images, but notice that the difference with supervised is that I'm not giving you labels. I'm just giving you the raw data, the images. And then in principle, hopefully your algorithm can sort them out in such a way that it makes sense that actually all these guys should be in the same cluster, but maybe the felines should be kind of like in this category and the transportation of the vehicles should be in this one. So this is what the algorithm is trying to make sense of. So clustering is not as hard, or at least the heuristics that people use, they work pretty well. But the type of unsupervised learning that I would like to emphasize here is what is called generative modeling. And generative modeling, the task is much harder because basically in generative modeling, the model, the robot is supposed to create. So basically the model, after showing many images of dogs, in principle, I'm supposed to be able to create dogs, not just to say it's a dog. Actually, I'm supposed to generate new faces or new images. So that's the difference. And you will see maybe now actually they're becoming more and more popular. In the classical domain, you will see this, that they actually, for example, if you heard about generative adversarial networks, so that's what I'm talking about. So that's a generative model, as it states in the name. We have restricted Boltzmann machines, RBMs, or we have variational autoencoders. So these are different kind of like models. Now we have autoregressive models. We have all kind of sort of recurrent neural networks, a lot of models that actually fit this category. And if you're curious about actually how that works, and maybe that is a little bit freaky, if you go to this website, thispersondoesnotexist.com, you will see a lot of human faces that actually, they don't exist. They just been generated by an algorithm, but they are very, very reliable and pretty much they look like humans. So in the quantum domain as well, we've been extending this. For example, one of the algorithms that the community has worked is about this QGANs, or quantum generative adversarial networks. There are this other idea of quantum Boltzmann machines, kind of like the extension. And there is an algorithm that we use extensively. This is the one that we proposed a few years ago. It's called the quantum circuit board machine. And basically what all these algorithms are trying to do is trying to make sense of the data, or the entire data set, and try to use quantum mechanics to generate images that look like the data set. So it's basically solving the same type of task. So that's just to give you a context of these particular models that I call quantum generative models. So with that, actually, with that framework, as I said, I'm going to skip the part where we use these algorithms to generate digits. That's just an application within machine learning. But I'm going to focus now on this particular publication that we posted this year about how do we combine combinatorial optimization with machine learning and with quantum computation. So that's basically what this work is about. So let me tell you how this work was motivated in the first place. So the motivation of this work is, if you look at the existing approaches for quantum optimizations, for the most part, they focus on solving a specific type of cost function. So when you're optimizing a problem, in particular, there is a type of cost function that is called a quadratic and constrained binary optimization. And basically, all this, in the binary optimization case, you have discrete variables, so they're binary, and the expression is quadratic. So basically, it's a polynomial of degree 2. And that's what basically, for example, if you look at the quantum heuristics proposed for solving these problems, so you find QAOA, that is one that you will see in the literature. It's called the quantum approximate optimization algorithm. Or quantum annealing, for example, company like D-Wave, that they have these devices that can solve also combinatorial optimization problems. Most of them, they deal with this type of cost function, a polynomial function of the binary variables, a cubo type of function. So basically, for example, if you ask the question, can they tackle large number of variables, like of the order of 500 or plus, or maybe 1,000 variables? But that's very typical in industrial problems. So QAOA, you say no. For quantum annealing, for the most part, is a no, just because, I mean, you need to embed these problems into the hardware. And then by the time you get to the sizes, pretty much, I mean, you're way beyond actually what you can do right now with the current devices. And then actually there is another family of methods that I'll be discussing this in more depth next, that is called quantum inspired. So in quantum inspired, actually the motivation is that they scale to large instances. And the reason is because they're cheating a little bit. They are actually they run on classical computers. So they have some quantum flavor. You can add some quantumness in the model, but in reality, they still run on classical devices. So that's why they're called quantum inspired. And they're built usually with tensor networks. So the beautiful thing about those models is that since they run on classical computers, they still, I mean, you can still efficiently simulate the quantum system, and then you can scale this beyond what you could do with hardware devices, with gate-based devices, or with annealing devices. Now, when you go actually to ask the question, can they solve an optimization problem with an arbitrary cost function? So what I'm referring here is to go beyond this polynomial expression. For example, let's say that you need to do a complicated integral or do a Monte Carlo simulation to compute a cost function. Like, for example, like in finance, you do some pricing and you're computing something complicated just to get a value of the objective function that you're minimizing. What you will find out easily is that definitely no. I mean, with QAOA, you need to have this strict cost function that is quadratic. The same for quantum annealing, because you're gonna map that to the device and the device requires that. And also for the quantum inspired proposals that are up to date, at least the other quantum inspired proposals, they also minimizing a Hamiltonian of this problem. I mean, an expression, an edge expression that looks like this, a cost function that looks also a quadratic or polynomial. So the other question that you can ask is, are these methods, do they get better as you get more data, as you get more evaluations of the cost function? And the answer is no. So basically what I will tell you about today is a new algorithm that was inspired pretty much to solve all of these issues. And basically this is what actually does what we call the quantum enhanced optimizer. So it's QEO. I will show you how actually we managed to work with large instances, work with arbitrary cost functions, and then take advantage of new information that is coming to the pipeline. And this is actually where the beauty of the generative models come into play. So the heart of this algorithm is a machine learning model compared to the other approaches. So let me tell you in a nutshell actually what this algorithm is about. And then, so this is the pipeline of how the algorithm works. So at the beginning, as in any optimization problem, you might have some initial observations. So you just might have some random guesses. From those random guesses or those initial observations of the cost function that you're trying to minimize, so you can actually build this blue histogram. So this would be the histogram correspond to the observations that you have. One of the tricks that we do within QEO is to bias the data, to apply a bias to the data in such a way that with high probability we'll be sampling those configurations, those proposals of the optimization problem that had the low cost. So as you can see in the x-axis here, there is a risk. And actually that means in this particular problem of portfolio optimization that we are studying, that would imply that I want to bias towards seeing or giving it a larger weight to those instances with the low cost. Now, that is actually the training set that I want to learn. And then I pass this to the heart of the algorithm. So the heart of the algorithm is this generative model that actually, since it is QEO, it is a quantum generative model, and that's where the quantumness comes. And basically, as I mentioned at the beginning of the slide, so you can use a quantum circuit generative model, you could use a hybrid approach, or you could use a neural network. So actually, this QEO in reality is a family of algorithms. So you could, depending which one you use, sometimes we refer to this algorithm as XQEO, and the X comes Depends if you use a classical, then it would not be actually a QEO. It would be a generative enhanced optimizer. It would be that specific exception is actually an entirely classical algorithm that it didn't even exist in the classical community. But then you could have even an entirely classical algorithm to compete against. But then you have actually the quantum one. You have a X could be a tensor network. So you have TN QEO, or you could have a quantum circuit, or you could have another type of model. Then actually, what is the generative model doing? So the generative model, what it's doing is absorbing all that data, the green data, the one that is biased, trivially biased. And then from here, the algorithm is absorbing that data. And as I show you with the robot, so it's absorbing images of dogs and it's generating new dogs. So basically what the algorithm is gonna say now is gonna create new data that is gonna look like the other data. So it's gonna still capture those correlations for which portfolios are the good ones, for example, in this specific example. And then it's gonna come up with new candidates. Those candidates, since they are gonna be different, those ones we need to evaluate the cost function, and then we add them to our loop of the data that we know by now. So we actually, we filter a little bit here. So we decide, okay, from this data, the ones that look more, the ones that satisfy, let's say, strong constraints are these ones. And then we pass them and we evaluate the cost function, and they just become kind of like, you can go this in cycles. So that's basically the heart of QEO. And as I said, I think the beautiful thing about this algorithm is that it's the first time that to the best of my knowledge, is the first realization, is the first demonstration where we merge the three fields: combinatorial optimization, machine learning, and quantum computation. So, and it works pretty well, as I'm gonna show you in the next slides. So the X, as I said, it depends on your choice. So the X is gonna replace, and we're gonna focus only in this talk on the case of the quantum inspired. So we're gonna use only tensor networks. So this X is gonna become TN for tensor networks. So when you see the TN QEO in the plots, that means that we are using at the core a quantum inspired model. So let me go with the yeah. So that's basically, we're gonna be using this tensor networks. So I think maybe I'm gonna skip actually most of the details, but for those of you who are technically inclined, or maybe are a little bit more familiar with the physics or what these tensor networks are about. So we use something that is called a Born machine, and it's one of the probabilistic models. So the idea of the Born machine is that you can load in this quantum object, in this matrix product state. That is one of these objects that you can come up with tensor networks. You can actually load probability distributions inside that object. And that's the probabilistic model that is actually capturing the correlations in the data. So at the core of the generative model is this Born machine that is built out of tensor networks. So these proposals, the proposal of the Born machine itself was actually the type of construction that we're using for this particular implementations is the one proposed by the group of Leiden in this paper, unsupervised generative modeling using MPS, matrix product states, if you're interested more in the data. And one of the beautiful things that we found up to this point, at the heart of QEO, as I mentioned, it needs to generalize. What is the concept of generalization? So the concept of generalization in machine learning is the most important concept when you train a machine learning model. Generalization means that you just don't want to memorize the data. So if I give you data and you memorize it, you're not doing anything with your machine learning model. Because then, for example, I give you a new image and you will not be able to tell that it's a dog, it's a slightly different image. Or for example, if you're generating faces, you would like to generate new faces, not just the one that you memorize from the model. So generalization actually in our model, if I pass the data and I load the data into this probabilistic model, I'm not doing anything. So I need to generalize. I need to be able to propose new candidates. So that's what it means, generalization, is the model is capable of giving me some new candidates. And what you can see here as the training is going in this particular plot is that our MPS at time t-2, that's the blue one. So we pass the data, so we train the model. When you train the model, now you are at t-1. You see that the model is different and it's leaning a little bit more like towards the left. And then in the next step at time t, that's the green one, the model is actually every single time that you're training and you pass in your data, the model is every single time shifting and shifting to the left. So that's the beautiful thing about this model and why it works in some way, is because it's generalizing. So this is the first demonstration that actually that these quantum models or quantum inspired models do generalize. And that's actually, that's huge news, because that's something that we didn't know in the first place when we started this research. There was just the hope, and we were just crossing fingers that it would generalize, but actually is doing it. And we have the demonstration here, and is solving this problem more efficiently than even as classical solvers, as you will see in the next slides. So one of the things that you will see from QEO is that, remember that in the table, I mentioned that the more data is a data-driven approach. The more data, the more powerful it is. So it's not competing with your classical solvers. So if you have a classical solver, we can just do it even better just by putting QEO on top of that. So if you're doing fine with you solve it, but you're just curious to see if you can do even better, so we can leverage all the data that you're generating. So it's not actually, it's complementary, it's a booster. So that's one of the modes of operations of QEO. And one of the things that you will see is that the real motivation between QEO, actually when I started this project, it was not only to solve all those challenges, but it was really what I was thinking, what was in my mind when I proposed this idea to one of my research scientists, is I wanted something that is more like Bayesian optimization. And Bayesian optimization, you have an arbitrary cost function. And also Bayesian optimization, you would use Bayesian optimization. It's one of the most powerful optimization methods. It doesn't scale, but it's really powerful. You would use it when you want to minimize the number of cost function evaluations. So that's important. For example, if you're working in energy and you're doing some oil drillings, for example, you would like to make the least amount of oil drillings before you find the eureka moment, because every single oil drilling most likely costs you millions of dollars. So when you have very expensive cost functions, you would like to have a friend who can give you the answer with very few probings. So that's actually the essence of QEO as well. It acts as a Bayesian optimization in the sense that it's building a probabilistic model at the heart. So that's why you see the heart of QEO is a probabilistic model. And the inspiration there that I came up with, it was actually inspired from how Bayesian optimization works. So let me give you actually a concrete example. So I already mentioned about the briefly in the last slides. Let me give you a concrete application. So it's not in energy, but it's actually in portfolio optimization. Maybe for those in the audience who are more inclined toward the finance applications. So there is actually a canonical, it's kind of like the fruit fly, or in the case of the fruit fly, the fruit fly is kind of like the well-studied case in biology. So the fruit fly of investment of portfolio optimization is this Markowitz model. That is the mean variance model. So it's an easy model, but it's what the first thing that you do if you want to understand something. And basically in this particular case of portfolio optimization, you're minimizing the risk. So that's indicated by this sigma square. So by this variance. And basically, so all of this is a covariance matrix that is telling you the correlations between the different assets. And here where you have the W is the amount that you would like to invest in the asset I. So in this particular problem, you have N assets. You have, for example, if you're talking about the SP500, we have 500 assets. So N would be 500. And the idea is that you want to optimize how much money, those are those weights, should I invest in each one of these possibilities of 500 in such a way that I minimize the risk of losing my money. But then I'm also very picky and I say, but I want to have a certain amount of return. So I'm fixing the return that I want to have on the portfolio. The portfolio is the construction of these assets. And then, but basically I want to minimize the risk. So that's why it's an optimization problem. So sometimes you can put even other type of constraints to make the problem harder. For example, you can say, well, I'm only interested in these certain lower bounds, this L. They actually indicate that you want to invest, let's say, not less than a certain amount and not larger than a certain amount. So you can have this type of constraints of how much you want to invest. But actually one of the constraints that makes the problem way, way harder, actually in this particular setting, is if you tell me, for example, that you want to invest only in 30 or 50 of the assets. So if you put a cardinality constraint that you say, I'm going to invest, for example, only in 50 assets, or sometimes the cardinality constraint is up to 50 assets. So, and this is because, and it makes sense from a practical perspective, because sometimes you have actually a cost associated with each one of these transactions. So one of the things actually that we explored in a previous paper as well in the case of quantum models is that the black curve here is what is called the efficient frontier. This R is the return, the expected return. So for example, if you give me a expected return of 2.5, you're trying to minimize the risk, the sigma. So the solution would be the black one. This would be the case under no constraints, under no cardinality constraint. But as I mentioned, the problem becomes very hard. Is constructing this efficient frontier is very easy when you don't have the cardinality constraint. But when you do have the constraint, the only option for you is to explore the universes where actually when you're constructing, for example, in this particular case of 4 assets, that you're restricting it to be just investing in 2 assets. So that's actually an example where the green curve is the solution from the green curve is different from the one that you obtain when you put the cardinality constraint. And this actually makes the problem highly non-convex. And that's what the problem is so difficult. So this is just to give you an idea of what is happening. For the case of the SP500 that we were able to run here, for example, if I give you an example of the SP500 with n equals 500, that we're gonna turn that into qubits in the MPS, and you tell me that you want to invest, let's say, on 30 assets, that gives me a search space of 10 to the 48, which is humongous, and we cannot do this exhaustively. I cannot compute all these lines exhaustively. It would be actually 10 to the 48 lines, and I cannot do that. So just quickly, because I think I'm running out of time. So one of the take-home messages is that QEO, in order to work, is generalized. And this is actually one of the real experiments that we did. So we have the blue one is the data that was coming from the portfolios that we explored, let's say we simulated annealing at some point. And then you pass this data to QEO, and the orange curve is the sampling from the MPS. So it's the sampling from the quantum spy model after training. And you see the beautiful thing that is happening here is proposing new candidates that not only they are new candidates, that's already surprising. It's not memorizing the data, but it's also proposing new candidates with a lower cost than the one that you had with the classical solvers. So that's why we say that that does not displace your classical solver. In reality, it enhances your classical solver, because actually this generative capability proposes new candidates which are valuable. So this is actually some numerical simulations that we did in the case of SP500. And this is what we call, the relative quantum enhancement is just telling you what is the improvement that you get compared to the classical strategy. So if you run your algorithm only all the way through with the classical strategy only, and you give them the same time to the classical strategy and to the quantum inspired strategy on top of the classical strategy, if you break the time in such a way that you can run still both, you still get an enhancement with the quantum model. And that's basically a 2% or 3% enhancement in the return, for example, or in the risk, actually. So this is about what you would get on these particular realizations. So I don't have time to go into the details of this strategy 1 and strategy 2, but basically the way to compare the details is that we're giving them the same time to the quantum inspired and to the classical model in order to do this. The final plot so this is actually some of the final plot that I was telling you is this idea of using it as a Bayesian optimizer instead of a booster. So one of the things that I mentioned is that you can use QEO as a standalone mode. So you don't need to have previous data. You can start from a random seed, and that's basically what we are doing here. And what we wanted, our target in this particular scenario is we wanted to be the best in getting the lowest value with the least amount of iterations, the least number of cost function evaluations. So what you see here in black is that QEO is finding actually, because it has this powerful probabilistic model that it's working with, is doing a more efficient search with the least number of steps that you would get with other comparable and state-of-the-art solvers like GPyOp, that is a Bayesian optimizer, simulated annealing, or a smart random that is not just, it's not just random, but actually it's a smart random in the sense that it uses the information of the problem to do a guess. So with that, I think, and I see already Vedran's face, so I would like to conclude. And basically, so as I said, I think we're super excited about these results in the sense that it's the very first marriage between quantum information, machine learning, and combinatorial optimization. one of the beautiful things that we find about QEO is that for the first time, we were able to prove that this quantum model generalized, that is actually something that wasn't known in this particular case, and on a very specific industrial application at the level of industrial scale, like the whole SP500. The scalability is we can go beyond like to thousands of variables easily with this quantum inspired compared to what we would do in a quantum hardware. The flexibility, as I mentioned, the fact that you can work with these cost functions, you can work with any cost function would do it as long as you have some discrete variables there. And yeah, so definitely, I mean, we're extending this to also even comparing against other state-of-the-art solvers, even entirely quantum model like the QCVN that I mentioned, or maybe extending to more complex tensor networks to see actually what's the power. And we expect actually to have even an enhancement. With that, I finish. And yeah, definitely, this is actually to thank the Quantum AI team at Zapata. This is the people, the current people right now. This has been busy time the past year for the most part, hiring and working with this amazing group of people. And then we are growing actually. So if you know of people excited about this research, we're hiring QML research scientists at different levels of leadership and also experience, ML engineers and quantum engineers. So thank you for your attention. I'm open for questions, or I don't know if we keep the questions towards after the second presentation. Thank you.
Thank you very much, Alejandro. This was very, very nice. And thank you for sticking with the time and even being a little bit strict on yourself. So the idea is that we have now a few minutes, even 5 minutes for the more technical questions. If somebody has really technical questions related to the research you presented, they can ask now. And in fact, we have some questions in the chat that I will now forward to you, and then we'll continue and do a reaction to both talks later. So we have one of the questions was, I think some 5 slides ago, you had a black curve to the leftmost.
This one?
No. I think it was slides before.
This one, yes.
Yes. What was the meaning of this black?
Yes, so the meaning in this particular portfolio optimization instance is what is called the efficient frontier. And this basically, I mean, one of the things that you realize is that if you don't put the constraints, this problem is entirely convex. And this actually you can solve with quadratic programming. And that's why you can get it really, really pretty much. I mean, you can get this. If you don't have the discrete constraints about the cardinality, this problem you can solve very, very efficiently. Actually, that's the trick that we do with QEO. So with QEO, we're dealing only with the discrete part, and the continuous part about finding the W's, that is actually at the end of the day what gives you this curve, is really we solve this very efficiently with quadratic programming. So the beautiful thing is the QEO is only doing the discrete search. Once you have a candidate and you tell me, this is the portfolio that I want to invest, but this is the assets, then I can go and find out the W's by solving this quadratic programming. And this is basically the curve. What it's giving you is actually for every specific return level that you specify here, this is actually the minimum risk that you would get. So that's why it's called the efficient frontier. So you cannot do better than this. And then if you had actually all the possible realizations here, where actually you're restricting, let's say, to only 2 possible, let's say 2 assets out of the 4, if you put the constraint, I want only 2, then basically you would get this curves, the different curves that you have here. And actually that is where you're looking now is at the crossing points, because those are the only valid solutions in this discrete space. So that's the difference between the black curve is the efficient frontier.
Thank you very much. And I think you've already answered implicit to the second question, which was whether the solution to this problem is efficient without cardinality constraints.
Yes, it is. Yes, it is, but it's just because we are using the toy model of the mean variance. But toy model is kind of like the first one that was introduced in the 60s. But it would not be actually, so it wouldn't necessarily be efficiently solvable if you had a more complex, for example, as I mentioned at the beginning, if you need to do a Monte Carlo simulation to find the pricing or the projection of what the portfolio will look like, then it might not be you might not be able to use a quadratic programming, and it might be expensive. And that's what actually, this is actually where you would really like to use QEO. When it is expensive, when it's not easy, is when you would really like to use it.
So I think we have a question related to this slide as well, and that's what's the meaning of the scales of this curve? I suppose the scales on X and Y axis, I suspect that's the question.
The 10 to the minus 3, so this is the risk. So that would be actually the risk as it is computing from the covariance matrices in some way from the, so this is actually, this covariance matrix is computed from the returns of the different assets. And then, so this is actually this expected return that you would have. So basically you just get the values from the stock market for each one of the assets. And yeah, so the scale is just actually, is the scale that is coming directly from the specific application. But at the end of the day, in terms of minimization, it's just, this is the return that you would get in these units. And this is, we're trying to minimize sigma all the time.
Okay, we have one question, which is, could you take a similar approach for identifying optimal models, or rather important variables for given data?
Can you repeat the question again, please?
Could you use a similar approach for identifying optimal models, or rather identifying important variables for given data?
Yes, absolutely. Well, yeah, one of the applications as well, that one of the combinatorial problems in machine learning that a lot of the people don't talk too much about is, I think maybe the person is referring to feature selection. So you would like to see actually what are the important ones. So, and feature selection is a combinatorial problem. Definitely, yeah. So that's one of the applications that we're exploring with QEO as well. Yeah. So definitely, so any combinatorial problem principle can be done, and feature selection is an ideal application again, because the difficulty of feature selection is that once you decide, okay, I'm gonna actually chop these variables, I'm gonna stick to these ones. Then, for example, if you're training a neural network model, that training is very, very expensive. And that's actually where you would like to minimize the number of calls to how many candidates you explore. And this is actually, again, with QEO is very handy. It's where actually is, you would like to reduce that. And that's why Bayesian optimization sometimes is efficient and explore for hyperparameter tuning, or for feature selection is not applied widely. It's just because it's so many variables for the most part, like hundreds or thousands of variables, that Bayesian optimization, you cannot do it. You can only do, this is the advantage of QEO against Bayesian optimization. In Bayesian optimization, usually all the papers that you see, they restrict to 20 variables or 15 variables or 30 at most, the most efficient ones. While actually QEO, you can go to 500. So that's why you don't see papers with using Bayesian optimization that much for feature selection, or at least I haven't seen. That's one of the reasons. It doesn't scale just because it's too expensive.
Wonderful. So just to stick with the time, we're going to now switch to the next topic, but any questions for Alejandro can still remain in the chat, and I will make sure to refer to them in the question answer session, which is going to be longer after the next talk. So at this point, it is really my pleasure to welcome our second speaker, which is Wim Van Ackooij, and he will be talking about computational hurdles in energy management optimization problems, and I will hereby invite him to give his presentation.
Okay, thank you. So I will share my screen.
So you're a little bit silent. I don't know if there's any way of.
Okay, can you hear me now? And can you see the screen?
We can see the screen.
Okay.
Yeah, but can you speak louder or closer to your mic, because the sound is very low.
Okay, I will try to speak louder then. And in any case, thank you very much for this kind invitation to give this talk. So in my talk, I will speak of energy management optimization problems. And I don't come at all from a quantum computing perspective. So I will look at some of these classic energy problems and try to show what can be done with classic optimization approaches, and also try to use this, of course, as a bridge to move into the, to build a bridge with the, what can be achieved through quantum computing, which maybe we can discuss during this discussion at the end of this talk. Okay, so I will try to give these several aspects of these energy management problems. And the idea of these energy management problems is basically related to various questions that an actor in the energy sector can ask. So I will try to give a basic introduction here. So the first question could be, for instance, what is a cost-effective energy mix? So of course, with the idea of this energy transition that is pushed in Europe, one can think what kind of assets should I build or invest in order to have a efficient and reliable system in the future. So this is a larger optimization problem where we can look at timescales in several decades. A second question could be how to manage existing assets, such as cascading reservoir systems. So this is hydro electrical power that exists. And well, these assets, they are naturally in a cascading structure. So when one uses a turbine at a specific level, well, water will be turbined and arrive in a subsequent reservoir, which is downhill and can be turbined again. And so this creates a certain coupling. A third question could be how to operate the system in near real time. We have lots of given assets. These are hydroelectric assets, of course, but also thermal plants such as nuclear or gas plants. Of course, also renewable assets such as wind turbines or solar panels. And of course, all of this has to be used in order to ensure that the user has its electricity at the end of the day. Upcoming questions are how to account for competition and upcoming structures in the energy system, such as local actors, but I will not insist too much on this during this talk. So with each of these questions, basically comes a temporal structure. So with this question of the cost-effective mix, we are looking at strategic planning. So what is the best strategic plan that we can come up with for the upcoming decades? When we look at this cascading reservoir system problem, we are looking at seasonal storage valuation, and we need to look at a time scale of the upcoming years. And this is related to the fact that the storage cycle for water is annual in nature. So we have the melting of snow in the springtime, of course, and then this water needs to be used during the year up until the next time that this water arrives again. At the short-term schedule, we have the unit commitment problem, and this is a problem of finding the most cost-effective schedule in order to ensure production for the upcoming days. So this is a short-term problem, but much closer to the physics of the system. So, of course, as a counterpart, the physics of the system will need to be represented with much greater detail. And I will not speak of upcoming problems in the energy sector. So in each of these levels, we have uncertainty which needs to be accounted for. Evidently, at the strategic level, uncertainty is somewhat of a different nature because one has to also deal with the impact of political policies, possibly climate change related issues. There can be financial uncertainty. There could be new technology which arrives in the upcoming decades and which will have a major impact on the system. Customers may behave quite differently in the future than they do now. And there can, of course, also be electrification. So as a good example of this is the push towards electric vehicles. Of course, if this trend continues, then in the upcoming systems, you have a great share of electric vehicles in the system, which will push the consumption up, of course. So this is something to account for. At the seasonal storage level, we have to deal with more classical forms of uncertainty, such as customer load or inflows, which have a weather-based component. So customer load, when it is colder, people will consume more electricity to heat their houses. And so there is an effect there. And of course, inflows depend on the weather, the amount of snowfall and rain and whatever more. So there too, there is an effect of the climate on the uncertainty. But this is more of a classic nature. This is more uncertainty in the idea of stochastic processes or random vectors or some more classical understanding of uncertainty. And of course, this is also the case for unit commitment problems where we have to also account for the uncertainty on intermittent renewable generation, which has a more short-term effect. And each of these problems can be seen as embedded one in the other in a certain degree. And so the seasonal storage level builds on the unit commitment level, and the strategic level builds on these other two levels. And so this can be seen as a very large embedded optimization problem where, of course, also these uncertainty levels stack one on the other. So classically, each of these big questions is somehow mapped to a big problem class. And I will try to give a short introduction there and try to showcase the structure of these optimization problems so that later I can indicate some of the structural properties of these optimization problems from a mathematical point of view and show why these are difficult problems to deal with. So in the strategic planning situation, evidently there is a question about the geographical scale that one wants to address. In case of the European situation, it might make sense to look at the European geographical scale. Of course, the time horizon is in some significant portion in the future. But we can also ask the question if we want to look at a dynamic situation. So if we want to figure out what is the best cost-effective set of assets at some period in the future, say in 2060 or something like this, do we just want to figure out what is this best cost-effective set of assets at 2060 without taking into account the entire history? Or do we also want to figure out how do we get to this ideal mix, say in 2060, starting from the initial set of assets, which is the current state of the system. So that would be a more dynamic situation to look at. That would, of course, be an optimization problem, which would be significantly harder than the static situation. Okay, so let me try to showcase some structure here. So I will use kappa, which is a sort of generic vector to indicate capacity, and which can be seen to be the amount of investment for various assets and various locations. So this is a vector, and we can arrange locations and assets types as we want, but this is supposed to represent all these investments that we can do. Then we have eta, which is an appropriately sized vector also, which represents meta-uncertainty. So here the idea is that experts can produce in a certain way reasonable or plausible scenarios for the future, say of political decisions or climate change scenarios. So here we can think, for instance, of these RCP 6 and RCP 8 and RCP 2.6 scenarios. And so we have these scenarios, but they come in as a discrete set, and it does not make sense to give them a probability. You just have a discrete set of these vectors and of these very large vectors, which indicate some assumptions about the future. And then we have this regular uncertainty vector psi, which depends in a certain way on this eta. For instance, if there's a certain climate change scenario, which we'll realize this may have a certain effect on the weather somewhere, for instance, precipitations, and this is maybe something we want to account for. So this psi of eta is indexed in this way. But otherwise, it is regular uncertainty. So depending on kappa and eta, we have the operational cost, which is how to operate the system at a given level of investment. We have also the investment cost, which is the cost of investing in a certain set of assets. And then the operational cost is in fact the solution of a optimization problem of its own, which consists in finding the best strategy of operating all the given assets, because once the factor of assets to invest in is fixed, then we just want to figure out how to operate all this. And this depends on, of course, on kappa, of course, on the meta scenario, and on regular uncertainty as well. And we want to minimize, say, the expected costs here. Then the idea of the strategic optimization problem is to minimize over all these capacities this cost of operating the system. So this is the strategic level. Now, what happens is that this operational cost basically stacks with the idea of seasonal storage valuation. So why is this a problem, a difficult problem? Because the idea of the value, say, of water is that it results from the substitution either in time or by other means of generation, because water essentially is, of course, free. But since if we do not generate electricity with a given amount of water, we will have to generate the same amount of electricity with something else, either in time or locally. And this is what induces a cost, or gives a value to the generation with water. And this value is further enhanced due to the fact that water is typically, or hydroelectricity is typically a very flexible means of generation. And so it is typically something which allows us to respond easily to unforeseen events. And so this gives us a further value. So here, the idea is we have a time horizon which will cut into further subperiods, smaller subperiods. Each one we will call it a stage. That doesn't really matter. And then we have this storage dynamics. So the idea is whatever we have in the reservoir at the beginning of the next stage is what we have already, plus or minus what we turbine here, plus the classic linear dynamics. But the difficulty of the optimization problem resides in the fact that we want to minimize the expected cost of operation of the system. So this C of S depends on the turbining strategy. We have some feasible constraints here. And here we have this difficult constraint in stochastic optimization, which expresses the idea that the turbining strategy can only depend on the information which is known at the time. So it cannot depend on yet unknown information. So it cannot anticipate the future. So this is written in this somewhat complicated way, but it is difficult to deal with constraint typically. And the operational cost C of S, what it is? Well, it is basically minimizing the cost of operating the system with all units. So now we have also thermal units here and renewable and whatever more, which are subject to their own feasibility constraints, so technical constraints here, and they all have to match load. This is seasonal storage. Last problem is unit commitment. So what happens here? We have a short time horizon. We have lots of assets. So here they are called M. So one asset here can be an entire cascading reservoir system, certain amount of time step, and want to minimize the sum of costs of generating with each of these assets, subject to the technical feasible solutions, all while ensuring load. Problem is that this set is typically not necessarily a convex set, making this a difficult optimization. Okay, so what is the classic approach to solving these problems? So why is this difficult, first of all? So we have various ingredients which make these optimization problems challenging. The first one is that we have uncertainty. This calls for methods from stochastic optimization. The second difficulty is that we have network-related structures, such as these cascading reservoir systems, which intrinsically link various components together. But we also have the transmission and distribution network, which needs to be accounted for. Then we have the need to represent the underlying physics of generation, and typically these are nonlinear, even non-convex, and so we can also have mixed integer decisions here. So we have also some integer variables, such as already seen in the slides by Alejandro. We have these binary variables here. We can have several of these, but also continuous variables, the amount of generation. And of course, we have these multiple timescales that we have already mentioned, and possibly some embedding of these different optimization problems, one in the other. So regarding the complexity, most of these problems are already very difficult. For instance, even the simplest forms of just unit commitment with just thermal units, no hydro, and very simple constraints are already NP hard, strongly NP hard. And it is also the case that some convex forms of stochastic programs can be NP hard as well. So when we combine all these previous difficulties, we have a challenging optimization. So how is this tackled? Typically, it is achieved by exploiting the inherent block structure of the energy optimization problems. So traditionally, by looking at the various time scales, so we have this strategic problem, which is decades, then we have seasonal storage, and then we have unit commitment. And then the idea is to sort of uncouple this in time and not have feedback loops and make simplifications. So typically unit commitment is done in a deterministic setting, for instance, and in the strategic planning, sometimes the physics of the underlying energy system are extremely simplified so as to make it all easier. But on top of that, we can also stack the use of classic optimization approaches, decomposition approaches such as Lagrangian-based decomposition or Bender-based decomposition. And the result of a combination of both strategies is that we end up with smaller chunks, smaller optimization problems, which can be tackled by dedicated solvers. So for instance, if we have a thermal unit which is optimized in a sort of Lagrangian decomposition scheme in unit commitment, then this can be solved by either some dynamic programming method or by a mixed integer linear programming approach. And the convex or concave parts, such as maximizing the Lagrangian joule, can then be done by using, say, cutting plane or bundle methods. So by using the combination of these approaches, we can sort of tackle these problems. So to give a small example, which I will sort of just show the size of what can be achieved with these classic approaches before trying to open up to quantum computing, is that we had this investigation of this stacking of unit commitment in seasonal storage in this EU-funded project called Plan for RES. So we consider a situation with 11 countries and a stochastic midterm problem with 78 stages, where each stage is further subdivided into hourly granularity. So this is the map. Say we have 7 reservoirs to deal with. So that is 7 reservoirs as a cascading structure at midterm and more than 1,000 generators. And this could be solved through our computer code, called SMS++, on a computer cluster in roughly 2 hours. And the next step, if we want to bring this even further, is to embed, say, this seasonal storage in the strategic level, and for each, this means that for each investment vector kappa, which I called kappa in this talk, we will have to solve the version of this seasonal storage. So evidently, if we want to do this iteratively, and we have to do this several times, then we will have to pay 2 hours of CPU time for each evaluation of kappa. And this also shows, of course, that there is a limit to what can be achieved with these classic approaches. And of course, there is the hope that through quantum computing approaches, we can push, say, the degree of realism of these models even further. So thank you very much for your attention. So if you want to learn more about these unit commitment problems, there is this survey that we did, which also deals with great many variants. And of course, the Plan for RES model is also described in this European project. So this is probably publicly available on the EU website. And well, thanks.
Thank you very much, Wim, for this wonderful presentation. We now have time for technical questions for you, and then one is already present in the chat, and then I will try to stimulate a little bit more discussion between Alejandro and you as well, just to see, I would like to hear how Alejandro feels about this very complex problem that you described. So the first question that we have for you is if you could give a little more detail on slides 11 and 25.
Sure. 11. Okay, let me get back. Yes, 11. Okay, so the so here we have this idea of strategic planning, right? So we want to find the best investment vector, which minimizes the sum of the investment cost plus the operational cost, which is induced at fixed investment. Now we have this question of how to handle, say, these climate scenarios or these meta-uncertainty vectors, and so there is an open element to this optimization problem in the sense that we need to give a good meaning to what we mean with minimizing this objective function. So one suggestion could be to minimize the worst case over all possible meta scenarios. So that means that basically you want to find the most robust investment strategy, which would be robust against all possible, say, climate scenarios. So even if RCP 8 or RCP 10 or whatever worst scenario happens, then it will work. It will still work out in terms of minimizing the operational cost. Of course, one could argue that wouldn't be reasonable cost effective wise, right? It may induce a very expensive set of investments. And what was the other slide? 25 was it?
Yeah, that was the slide 25, yes.
So I hope to have answered the question regarding slide 11. So this is just to show, by the way, this was just to show the map of the 11 countries. And these camemberts, I don't know what is the pie charts. These pie charts show the percentage of generation with different means of generation on average at the yearly level.
And just to double check, when you say the solution is then the corresponding kappa vector for this particular scenario that is here described in detail?
In this problem, kappa is fixed because we do not yet optimize kappa. In this problem, what we are interested in is finding the best way to place the available hydropower over a yearly time horizon. So this is the initial step moving towards strategic investment. So of course, this can be used to evaluate two different kappa strategies, right? If you have one, you plug it in and you evaluate the operational cost with this computation. If you have another, you can do it again, and you can compare and figure out whatever investment strategy is preferable.
Very good. So there's a lot of sort of nested structure and expensive subcalls here. So I'm wondering if Alejandro maybe sees something which is resonating with the types of ideas that he's been expressing in his presentation. Maybe Alejandro, if you have a comment.
Yes, one of the things, I guess, I think there is an echo from Vince. Microphone. Yes, so. Yes, okay.
I will stop sharing and then maybe I
can. Thank you. Yeah, so what I see, I mean, I think definitely the mixed integer linear program. I mean, I think the mixed integer type of problem, I think that's something that is interesting. Yeah, the fact, I mean, one of the things that we're trying with our quantum enhanced optimization, and this is a challenge for any of the quantum optimization strategies, is to work with real continuous variables. Because as I said, the portfolio optimization is a special class in the sense that you can break, and actually this is what all these meta-heuristic state-of-the-art solvers of portfolio optimization do. You can break it into a decision piece. That is the one that I mentioned. Do I invest? In which ones do I invest? That's a 0-1 type of question. And the other part is the one that you can go and evaluate, and that's the quadratic programming piece. So I think, I mean, the problem has that structure that's already native, let's say, for our algorithm. So we just need a discrete part being the hard one, and then we're good to go. But for the case when you have even continuous variables, I mean, the original problem of portfolio optimization is solved with continuous variables. But let's say you have a problem with all the, we're dealing with customers now where actually they have an optimization problem. Maybe it's the case here where actually all the variables really matter. And the problem is really of a nature of a continuous nature. So in reality, you just need to find out. There is no way to drop a priori or to even to make this a decision type of question. So in that aspect, yeah, so there is a version that we've been testing that is actually that you can work with continuous variables. But there is the challenge when you have purely continuous variables. And that's where the mixed integer, that's the one that I would say it's promising as well, but I think it's something that we're testing, like when you have actually continuous variable in your case. So I don't know, Wim, if in your case, your type of problem is similar to the portfolio optimization where you can break it into a decision problem, or you can isolate only the discrete part or the integer part and say, okay, I'm gonna solve the integer part and then complete with the continuous with a different type of solver, or is it actually is all mingled and it's all entangled in some ways the whole problem?
Yeah. I mean, when the underlying optimization problem is a mixed integer linear program, then you can always attempt something like Blender's decomposition, right? You can always put all the binary restrictions and variables to the master problem, and then you have a slave problem, which is a purely continuous one. So this can be, you can somehow isolate the required structure, but the difficulty then would be that for certain integer restrictions, the continuous problem will be infeasible. And so typically you will have to add what in classic Blender's decomposition is called feasibility cuts. The dumb version of that being the no good cuts. Basically, you evaluate a binary set of vectors, and then you figure out, oh, this problem is infeasible, and then you just forbid this specific allocation. You just say, okay, at least one of these binary variables needs to have another value. And this is a very inefficient way of proceeding, of course, not computationally very promising. So what I would like to ask you, Alejandro, then is, do you think that, I guess in your optimization portfolio problem, for every binary allocation, the problem was feasible. Do you think that you can make an adaptation of the procedure where you might not have this assumption?
Yes. So I think I was briefly mentioning that in answering one of the questions is let's assume, for example, the case of portfolio that actually you still do the decision, but let's say to estimate the weights, the continuous part, let's say that is very difficult to do. Actually, it's intractable, as you pointed. Maybe, for example, let's say that you need to do some highly complex Monte Carlo simulations in order to determine these weights in a particular scenario. You need to compute maybe a complex integral that actually maybe you need to approximate, and it's very, very expensive. So those cases is where we feel even still solving the discrete part, as long as the discrete part is intractable, it still pays off. And the reason is because what the generative model is helping you is to navigate efficiently the discrete space, that is the complex one. So in some ways, capturing the correlations between the solutions and understanding somehow what's the structure behind the good solutions. Remember that I mentioned in my algorithm, in the slide about the algorithm, that there was a bias towards the good solutions. So that bias, the bias is trivial. In some way, we just do it with there is no computational cost to doing this bias, but it's just to favor, just to indicate, to guide the algorithm to say, you should be paying attention to these leading solutions, the ones at least that we have explored thus far, in such a way that you make proposals that look like these ones. So that's really, in some way, the way to imagine this is imagine that you mentioned that maybe that's not with the standard solvers, that's not an efficient way. but in some way with QEO, you can imagine as having an algorithm where actually with the memory of the algorithm is very long. So you're exploiting all the data that you're seeing as part of your next candidate. Well, actually, most of the algorithms, they forget very quickly. For example, if I think of simulated annealing or parallel tempering, that they are used also to explore the space, they usually take into account the previous iteration, or they have very short memory in some way. But actually, in QEO, you are actually leveraging on all the data that you've seen thus far just to capture those correlations. So the mentality is different, and that's why I mentioned maybe it's closer to Bayesian optimization. Where in Bayesian optimization, you load all the data, and the more data you see, the more information you get about the cost function in some way. So you're unveiling that structure. So I think it still will pay off, even the case where you have an infeasible part that is the continuous part. You still need to make your best guess and I guess try to solve it somehow. But then it will still reduce you the number of steps that you take in the discrete part. So as long as the discrete part is still large and combinatorial and maybe worth using an optimizer, I think you will still see a benefit. Even in the case where you have actually a non-feasible continuous piece.
Do you have some experience in solving mixed integer linear programs with the?
I haven't tried it with this one, so yeah. So and to be honest, I haven't played too much with with this type with the mixed integer linear programs. Yeah, so we haven't actually. This is not one of the cases that we have studied thus far. Yeah, but it would be interesting to see benchmarking against. I mean, there were some difficult benchmarks there. I think that's the other thing. In quantum computers, sometimes we find ourselves recycling the methods that actually usually don't work. Oop, I think I hear the echo. Let's see. Yeah, there you go. Yeah, so we find actually ourselves usually recycling methods in computer science that they dropped just because they were not actually feasible. And the reason is because those are the most exciting ones for us as quantum computer scientists, is because we want to find, as I was mentioning in my motivation slides, we are usually find ourselves recycling these papers by Jeff Hinton in the 80s and doing adaptations so that way they dropped it because there was not a computational algorithm to solve them. And the reason is because we really would like to see that. So one of the things to keep in mind in the benchmarks is that in the benchmarks that we do, if the benchmarks are hard, that's the most exciting for us because that's where we can see we can actually see advantage because it's really hard to compete with these highly tailored classical solvers. So for example, if we had something like a mixed integer linear programming type of data sets that we know is intractable, not only in hard, but they represent, they are known to be super, super hard instances. I think that would be exciting. That would be exciting to know, and that would be exciting to test. As I said, the type of problem that we chose even in portfolio optimization is an odd case just because of in some ways, the easiest problem within all the versions of portfolio optimization is this Markowitz mean variance model that is very well studied, is the most studied problem. And you see that the percentages where we were squeezing some advantage, it was actually when you get to 500 variables, when actually the problem is very, very intractable and all the other solvers get lost in the search space. So the larger the size, the better for the quantum algorithm. But what we are usually going after in quantum computing, or at least from the applications for looking for quantum advantage, is this, and I don't know, like maybe I didn't see a sense of I couldn't count properly like the number of variables in your problem, but it would be the smallest and the hardest the problem, the better. I think those are the ones that we're ideally looking after. So like on the order of 100 or a few hundreds, and I think those are the ones that are the best in the sense that we can have a chance to solve it with these technologies in the near term.
Maybe if I can add as a part of a question to Wim here. So in your type of approach, in your research, I mean, you developed various down the line heuristic methods, right? You don't find optimal solutions to this thing, right? You do this all partitioning, the composition techniques. How do you know how well you do? How do you benchmark? I mean, if Alejandro was to say, okay, I'm going to do something here, what would be sort of the type of thing that you would expect a researcher to tackle?
We do have actually idea of optimality and proof of convergence. I mean, in the usual decomposition strategies, what you do is you typically generate a lower bound on the optimal value of the optimization problem. And so as soon as you generate a feasible solution, then you can actually evaluate the gap with the best known lower bound and figure out the quality of your solution. So also in classic mixed integer programming, you have continuous relaxation, which gives you a lower bound. And so even though theoretically you know that your algorithm will converge because eventually you will explore the entire search space, usually at each stage you have a guarantee of quality. You know that whatever feasible solutions you have at this stage, well, they are at this gap from the optimal solution. So some of the classic unit commitment problems, not with hydro, but purely thermal, if they are formulated as mixed integer linear programs, we can actually solve some pretty impressive instances and have a pretty decent optimality gap. So I don't know, 100% is typically achievable then. Of course, if you want to look at strategic planning, then it doesn't make sense to have 100% of optimality gap. I mean, there's, well, you have to find all sorts of data and there are all sorts of assumptions, and you would be happy with 1% or maybe 5 or whatever, right? You're happy with another gap. But typically, there is an idea behind all these decomposition approaches and also in convex optimization, of course, to be able to provide a quality guarantee for the solution provided. This is also something of interest, of course, for the if you want to sell it to the CEO of the company, right?
Right. Mm-hmm.
So yeah, I wanted to jump back on the thing that Alejandro said. Did you benchmark the approach against mixed integer quadratic programming, which you can do with Cplex, say, or Kurobi, the quantum approach?
No, we haven't. So I said, I mean, this is the very first application that we tried. So the algorithm was new, and at least, well, the person actually that we co-developed the algorithm that we implemented actually had a background in finance. So we decided just to go straight with this application. But actually, we're currently working even with concrete customers, actually with industry partners that actually they come with the problem and they have the state-of-the-art solver. So that's an exciting collaboration as well for us to work with industry partners when they come as customers and they're interested in testing it out. Because we know, like as in your case, you had the best heuristics and you know you're probably in and out. So those are the best actually people to work. So I think, yeah, back in the day when I was working with the D-Way devices for many years, so definitely we would resort just to kind of do benchmarks on graph problems. And at some point, I mean, I think at NASA, I certainly worked with fault diagnosis problems that were kind of like more like close to the real world scenarios. But yeah, but definitely that's something we haven't tested yet. And so we're slowly increasing kind of like the type of algorithms that we don't know like where it would excel. That's actually one of the things that we are testing. So we're surprised to see these results. We actually we hired a consultant actually who is the expert in this portfolio optimization type of instances, and we are doing some benchmarking against the state of the art even within this particular application. So that's my passion at the moment, kind of like going for showing that we can do something better than actually this classical algorithm. So certainly we're expanding the pool, and yeah, I'll keep an eye on this. Keep an eye on maybe some data set. And if you have any data sets that you feel they're super hard, that they share these properties, yeah, be happy to give it a shot as well in the future.
Yeah, I mean, I think it would be interesting to see what can be achieved if we have this mixed integer linear structure and we try to use this trick of isolating the purely combinatorial parts from that and have the more continuous part in a sort of packaged version. This is what I picked up from your talk, that this is the way you look at the problem. So that can be arranged for some of these optimization problems. So it would be interesting to see what can be achieved then in terms of numbers of variables and precision and whatever more. But
definitely.
of course, I mean, the unit commitment problem is a very old problem. This is something that has been, that people have been working on since 50 years or more. So evidently there has been progress made in the size of instances that can be solved, which also scale with the computer power, which scaled at the same time. And also the, I mean, CPLEX also, this is a nice example, right? CPLEX is much faster today in the size of problems that it can solve because of not only computer power, but also of better algorithms.
No, thank you, Wim.
And with these words, I think it is very sad that we have to call it a day because we're now out of time. I want to thank you both for your wonderful contributions, and I will give the last word to our host, Pascal.
Thank you. Thanks to all of you. Thank you, Vedran, for moderating this webinar. Thank you, Wim and Alejandro, not only for your presentations, but for the exchanges between you both. It was really interesting. Well, this is all I have to say. Nothing to add. I know we're standing between you and your weekend, so I will just say that I hope to see you at our next webinar next week on Friday that's dedicated to quantum finance. So if you have an interest in quantum finance, or if you like us, we hope to see you next Friday. Thank you all. Bye-bye. Have a good weekend, and you will receive the recording of this webinar.